Hello guys, welcome to Physics Grad. In this video, we are going to see a series expansion formula for a finite canonical transformation which depends on a parameter. So let us begin. So we begin by recalling that there are two views with respect to which we can understand a canonical transformation, and one of them is the active view, in which a canonical transformation takes us from one point in a phase space to another point in the same phase space. Okay, so which means if we have a phase space of generalized momentum and coordinates, and this is where the system is initially, we perform a canonical transformation on this particular configuration point, and the canonical transformation takes us to another point B in the same phase space, in contrast to the passive view wherein we move to a new phase space which is defined in terms of the new generalized momentum and coordinates, and all of these have been already explained in the previous lectures. So in this video we are going to derive the series expansion formula for a finite canonical transformation which depends on a parameter. So to explicitly make it clear, let me write that down. So we consider a case where the finite canonical transformation is parameter dependent. So before we move further, let us try to understand when I say what it means when I say that the canonical transformation is parameter dependent. Okay, so we know that a canonical transformation is basically writing our going from the old set of generalized coordinates and momenta to a new set in such a way that the form of the Hamilton's equations of motion is conserved. Okay, so let the vector psi denote the new set of generalized coordinates and momenta, and what canonical transformation equation is going to give us is, it gives us the new momenta and coordinates in terms of the old momenta and coordinates. And since we are saying that the canonical transformation is parameter dependent, in this equation we are also going to have a parameter which I am going to call alpha. Okay, so what is the significance of alpha being present in the canonical transformation equation? That is going to play a significant role when we derive the series formula. Okay, so this alpha is our parameter and eta is the initial coordinates and momenta. Okay, now when I say that the canonical transformation is parameter dependent, what it means is that if I change the value of alpha, then I am going to land at different points in phase space from the same initial point A. Okay, so that means, let's say that I choose alpha to be equal to alpha b, then this particular equation takes me from point A to point B in the active view. And if I choose alpha to be some other value, alpha b dash, then I am going to go from A to some other point B dash in the same phase space with respect to the active view. Okay, so therefore by choosing different values for alpha, we are going to different points in the phase space in the active interpretation from the same point or starting point A. And this is the meaning when I say that the canonical transformation is parameter dependent. So the form of the equation contains alpha as one of the parameter, and by changing the value of this alpha, the values of the new coordinates and momenta are also going to change, even if we keep our initial momenta and coordinates the same. which turns out to be going to different points in the same phase space for different values of alpha. Okay, so let me write that down. By using different values for alpha, the canonical transformation takes us to different points in the phase space from the same initial point. Okay, so from this you should have been able to understand what it means when we say that a canonical transformation is parameter dependent. Okay, so in terms of the active interpretation, it basically means that we are going to different points in the same phase space from the same initial point. So therefore we can construct the finite canonical transformation as a series of infinitesimal canonical transformations by changing alpha by a small amount d alpha. Okay, so let me explain what this statement means. So we already saw that in the active interpretation, a canonical transformation takes us from the initial point A to some final point B corresponding to the parameter value alpha equal to alpha b. Okay, but we saw that for such a transformation which is parameter dependent, by changing the value of alpha, we are going to go to different points in the phase space. So from the initial point, let's say that at the initial point our value of alpha is equal to 0 without any loss of generalization. So now what I'm going to do is I'm going to change alpha by a small amount, which means our canonical transformation is going to go to another point in the phase space, but that point is going to be very close to the initial point A. And that is the meaning when we say that the transformation is infinitesimal canonical transformation. So if I keep performing this transformation again and again on the transformed coordinates, I am going to eventually have a series of infinitesimal canonical transformation which may lead us to the finite transformation from A to B. So what I mean by that pictorially is that as I perform an infinitesimal canonical transformation on the points A, I am going to reach some point close to A. Again, I perform the infinitesimal canonical transformation and so on. I keep doing that, and this leads us to some kind of a continuous trajectory in the phase space and finally may end up in B, depending on how exactly we construct this series of infinitesimal canonical transformation. And I'm going to soon explain the details of the same. Okay, so this implies that we now move, okay, the system point along a continuous trajectory, in phase space. Okay, so when I tell this, the following questions may arise, and we are going to answer these questions one by one in this video. So question 1, how do we choose this trajectory? Okay, how do we choose this trajectory? Now remember, this is not the mechanical path taken by the system as time evolves, but rather this is our active interpretation of a particular canonical transformation. In fact, this is a series of infinitesimal canonical transformation which behaves or which looks like the system is moving along a continuous trajectory. But this is not what is happening in reality. In reality, the system takes a path which is followed by the Hamilton's equations of motion. Okay, this is what our active interpretation is telling us. Active interpretation for the canonical transformation. Okay, you have to keep that in mind. So another question that you might have is whether is this path unique? Okay, is it unique? Is this trajectory unique? Is this the only way through which we can go from A to B through a series of infinitesimal canonical transformations, or are there more than one ways? Okay. Question 3. What does this trajectory depend on? Is this trajectory completely arbitrary, or are we constructing it based on some dependence on some function or a parameter or a variable and so on? So we are going to also discuss this question. Okay, so what does this trajectory depend on? Question 4. How do we choose alpha? Is the parameter alpha completely arbitrary, or whether it depends on the problem and whether there is some restrictions on the physical dimensionality of alpha or not? Okay, so this is the fourth question that we are going to answer. So how do we choose alpha? So keeping these 4 questions in mind, we are going to continue, and as we move on, we are going to slowly get the answers to each of these questions. Okay, but since this is part 1 of the video, this particular question will be better understood or better answered when I make part 2 of the video, which is going to explain some of the examples on this concept, and whether the trajectory is unique or not, you will get it when we explore those examples in the next video. So this will be answered in the next video. But the rest of the 3 questions, we will be answering them as we move along. So now let us consider a function u. Okay, so let u be a function of system configuration, which means that it depends on where the system is present in this phase space. Okay, so the value of the function u at point A will be dependent on the point A, and the value at B is also going to depend on the value of P and Q at B, and so on. Okay, so this implies that u will be a continuous function of alpha as well along the trajectory. Okay, so what this means is that since u is a function of the phase space coordinates and momenta, as we move along this continuous trajectory, the change in the phase space coordinates and momenta are also going to be infinitesimally small, which means the change in our function u is also going to be very small, or in other words, u is going to be continuous along this trajectory. And also, since this trajectory depends on how we change the parameter alpha, our function u in turn is going to depend on alpha. Okay, so therefore this implies that u is going to be a continuous function of alpha along the trajectory. Okay, so this can be written as u of alpha with the initial value u naught being equal to u of 0. That is, at the point A, when alpha is 0, let us consider that the function u has the value u0. Okay, and for simplicity also we are going to consider there is no explicit time dependence for this function. Okay, so with these things in mind, from one of our previous lectures we have seen the following. Okay, so then we know that the change in the value of the function u is given by some infinitesimal number times the Poisson bracket of u with respect to a function g, which is the generating function for the corresponding infinitesimal canonical transformation. Okay, so let me make that clear. So here g is the generating function of the infinitesimal canonical transformation, due to which system configuration changes and therefore u changes. Okay, so g denotes the generating function, and this epsilon is just an infinitesimal number. Okay, and this relation has already been derived in our previous lectures, one of the previous lectures. Okay, and what we are going to do here is we are going to choose, since epsilon can be any infinitesimally small number, we are going to keep or choose epsilon as equal to d alpha, which is the change in the parameter alpha by a small amount. Okay, so what does this tell? What does this tell us? Finally, we have the change in the value of the function u is equal to change in the parameter alpha times the Poisson bracket of u with the generating function g of the corresponding infinitesimal canonical transformation. Okay, so now if you observe, we already have our answer to two of our question, that is this particular question and this particular question. So by choosing our g, we are basically choosing the trajectory. Okay, so note, I'm going to explain this more clearly. Answer 1 and 3. Okay, the choice of g fixes the trajectory. So what this means is that if we are in some initial point in the phase space, and if I choose a generating function g1, then this particular generating function is going to take us to an infinitesimally close point in phase space. Let us say that, so if this is the point 0, let's say that this is the point that we get when we perform an infinitesimal canonical transformation by choosing a generating function g1. Similarly, if we choose some other generating function, we will end up in some other point g2 or point 2 where we have chosen the generating function to be g2. Similarly, for g3, we will end up in some other point 3. So the point where we are going to end up in is going to depend on the choice of generating function, and the position of the point is basically going to determine the shape of the trajectory, and therefore whether we are going along this trajectory or whether we go along this trajectory is going to depend on what choice we make for the generating function which is present in that Poisson bracket relation. Okay, and once we have chosen this generating function, we know that in physics every equation must be consistent with physical dimensions, and once we have chosen g, we fix the dimension of this guy and this guy, which means we are fixing the dimension of alpha. Okay, so that answers our final question, which was how do we choose alpha. So answer 4 is that G fixes the dimension of alpha, and the physical significance or the physical meaning of alpha we will have to get this from the problem which we are facing. Okay, that will be problem dependent, and this will be understood more clearly when we discuss the examples in our next video. Okay, and the physical significance of alpha depends on the problem. Okay, so to quickly summarize, the choice of G is going to correspondingly choose a particular trajectory for us to go from point A to point B, and the choice of G is also going to fix the physical dimension of alpha, which in turn gives us some idea to impart some physical meaning to the parameter alpha depending on the problem. Okay, so this will be more clearly understood as we discuss more examples. Okay, so now continuing further from this relation, I can write du by d alpha is equal to Poisson bracket of u and g. So this is going to be an important relation which we need to remember for the further derivation. And in a similar manner, so similarly, we can write d by d alpha of du by d alpha is equal to Poisson bracket of du by d alpha times g, where basically I have replaced u in this equation with du by d alpha in this equation, which is going to give me, if I substitute using this equation here, this is going to give me the following Poisson bracket relation. Okay, and so on for higher derivatives. So we are almost there. So because of this, since u is a continuous function of alpha along the trajectory, of course, we are going to express u as a series expansion using Taylor's expansion. Okay, so using Taylor's expansion, we have u of alpha will be equal to u naught plus, so we are expanding this function with respect to the initial point, so this is going to be equal to u naught plus alpha times du by d alpha at the initial point plus alpha square by 2 factorial d square u by d alpha square at the initial point plus alpha cube by 3 factorial d cube u by d alpha cube at the initial point plus, and so on. But from these relations we can replace the derivatives using the Poisson bracket relation as follows, and what we get is the following. So we know that du by d alpha at the initial point is nothing but Poisson bracket of u and g at the initial point, and d square u by d alpha square at the initial point is nothing but this Poisson bracket relation at the initial point, and so on. Okay, so using this relation we can therefore write u of alpha is equal to u naught plus alpha times u g naught plus alpha square by 2 factorial u g naught plus alpha cube by 3 factorial u g G naught plus so on. Okay, and this is the final expression or the series expansion formula for a function which depends on the system configuration, which means it in turn depends on alpha, and therefore it is a continuous function of alpha along the trajectory which takes us from the initial point to the final point B. Okay, so now if we choose u of alpha to be equal to any of the new coordinates or momenta, or the transformed coordinates and momenta, with u naught being equal to eta I, that is the corresponding initial coordinate or momenta, what we are basically getting is nothing but the canonical transformation equation. Okay, why? Because let's say that this epsilon, not epsilon, this psi of I is nothing but, let's say, P1B. Okay, that means this is going to be P1A, that is the initial generalized momenta, and this is the final generalized momenta for the canonical transformation. So if we make this particular choice, and for the suitable choice of generating function and alpha, which will be more clear as we discuss the further examples, we are going to basically get P1B as a function of some function of P1A and G and P1B, and since the Poisson brackets involve differentiation with respect to all the initial coordinates and momenta, we are going to also have expressions involving all the other initial coordinates and momenta for I not equal to 1. Okay, which is nothing but our relation for the canonical transformation of for going from A to B. Okay, so basically what we have done is we have found a relation for a finite canonical transformation as a series expansion in terms of Poisson bracket, nested Poisson brackets in fact, and these Poisson brackets involve generating functions which generate a series of infinitesimal canonical transformation which basically transforms into being a continuous trajectory which is taking us from the initial point A to final point B, and therefore giving us the relation for the total finite canonical transformation from A to B. So I hope that you have understood that. So therefore we get the series expansion formula for the finite canonical transformation. Okay, so before I end this video, I want you to observe the following structure of this equation. Okay, so if you observe this equation, this has a very close resemblance to the series expansion of an exponential function. Okay, so let me just write that down here. So note, the series resembles the Taylor's expansion of e power x. The Taylor's expansion for e power x. Okay, so to see this, let us consider the following. The nest of Poisson brackets in the nth term can be considered as the nth repeated application from the right of the operator defined by this manner. Okay, or when we say nth repeated application, it is same as saying nth power of that operator. Nth power of the operator. So this implies that I can write u of alpha as equal to u into e power x hat times alpha at the initial point 0. Okay. So what this means is that if we this is nothing but u naught plus alpha times u x hat plus alpha square by 2 factorial times u x hat square plus alpha cube by 3 factorial times u x hat cube plus so on, where our x hat is nothing but this, the operator given by this particular relation, and x to the power n is the nested Poisson bracket, which is nested n times. Okay, so here we have n times, which basically gives us u naught plus which basically gives us the same relation as what we have given here. Okay, and we will come back to this resemblance when we study quantum mechanics, wherein especially we study the Heisenberg's picture of quantum mechanics, wherein operators evolve with time and the wave functions are kept constant with respect to time. And what we see is that the Poisson bracket formulation of classical mechanics is analogous to the Heisenberg formulation of quantum mechanics. So thank you for watching and see you next time.